Yeah, let's continue what we were doing. So last time we started doing a basic hypergeometric series. We started looking through some summation formulas where some special forms of series were turning into products. And with that, we were able to prove a couple of the things that we already proved using combinatorics, but it was just a lot of combinatorics build up that we needed to do beforehand. Now with these hypergeometric sums from a different angle, they became easy. They became consequences of the Q binomial theorem, right? So let me remind you of the Q binomial theorem. So Q binomial, and although the binomial coefficient or the Q binomial coefficient are not defined right now, I will define them and we will see the connection once we get to that. So this is the Q binomial theorem. And it is a single sum n from 0 all the way to infinity. On the bottom, you have a Q-polymer QQn. The base is always the same. On the top, you have AQn. So you can pick what A is supposed to be. And you have a z to the power n, an argument. And this thing turns into a product, which is AZ base Q sub infinity and Z base Q sub infinity. Okay. So here's this one main theorem, and we were able to prove many things with that. One of them was just plugging A to be 0, Z to be Q, right? One corollary was that partition generating function that we saw many times. A is 0, Z is Q. We already have that. This sum Qn divided by QQn and from 0 all the way to infinity is A0. So this guy goes away. The product is, if I should remind that, A sub Q sub n is 1 minus A, 1 minus AQ, all the way to 1 minus a q to the power n minus 1. And if that n is infinity, this tail just goes to the infinity, right? And if a is 0, all you get from these parentheses are just ones each. So you end up getting a 1 on the numerator, and I plugged in z to be q, that became q infinity, right? So this one, we needed to just say that q to the n is one column of n things, then the next piece, 1 over QQn, is the generating function for partitions into less than or equal to n parts. And we need to combine many things. But with this one formula, Q binomial theorem, we actually get 4 of these previous formulas that we proved combinatorially. Okay? It is not to say that the hypergeometric summations are stronger than combinatorics. It is to say that there are different techniques that we can use, and all of them have their advantages. In combinatorics, if you can construct this combinatorially, then perfect. You know what every piece of your generating function does. And you can build bijections on top of it. You can build more things on top of it. If you know the summation formula, that's also just as good. Then you can get generating function connections through that. And sometimes some techniques are going to be more useful than the other ones. That's just that. And yeah, another one that I want to remind you, another formula that I want to remind is this guy, which we have proven last week as well. So x to the n, q to the n to the power 2 divided by q squared n, and from 0 to infinity is minus x q to the power 2 sub infinity. Right, we take q goes to q squared in Q binomial. For the proof of this in Q binomial, we first take q goes to q squared. Okay, then for that square, we needed z to be q over a. And then we take a goes to infinity and use this limit, which is also a really helpful limit. Good to keep in mind. So maybe a red. So limit as rho goes to infinity of rho base q sub n divided by rho to the power n is -1 to the n q to the n choose 2. So it is n minus 1 over 2. So a good limit, a good formula that we will use today, a really strong theorem that will be core of things. This x, oh, that is what I meant. So this x, for that formula, we would need that x, yeah. So z and x is just a bane to my existence. I keep on mixing them in q difference equations. I keep on using both x's and z's, but this is what I meant. So in this formula, plug in xq over a, so you get that x to the n, you get that q, which will cancel this -1 at the very bottom when you take care of that. And then this a goes to infinity, you end up canceling this top factor, right? And that is going to take care of everything. Yeah, on the bottom you would have, so over here, like look at the product side, az base q is going to turn into, let's put a minus even. Apparently I was missing that as well. I was quite focused on what the limit should be. So I forgot the x, I forgot the minus. So z needs to be minus xq over a. Is that better now? There's this minus. So q goes to q squared. So these bases all became q squared, right? That is fine. Then when I plug in minus xq over a, let's look at this product. Minus xq over a is going to turn into a minus xq because that a is going to cancel with the denominator, right? az, so multiply with an a, that is going to cancel. We will get this part, correct? And on the bottom, we will have minus xq over a. So if a goes to infinity, that a will go to infinity, this term will go to 0. So 0 base q squared infinity is just 1. So the denominator goes away. So there's that missing denominator, which is 1. And on the right, that minus will already introduce a -1 to the n. So when I take the limit, I will end up getting another -1 to the n. They will cancel out. Because my q was q squared already, I don't have this division by 2. Let's do it. So let's do the proof. I will raise it here, and we already did it last week, but it's always good to do that once again. So the first step is take every q to q squared, right? I mean, I take the q binomial, write everything with q squared. A q to the power 2 sub n divided by q to the power 2, q to the power 2 sub n. Then we have z and a z q to the power 2 sub infinity z q to the power 2 sub infinity, and goes from 0 all the way up. Okay, now the next step is we will plug in z being minus xq divided by a. If you don't mind, I want to do that here. So instead of this, I will write minus xq divided by a, right? Here again, I'll write minus xq divided by a. And here I will write that minus xq divided by a. Is that okay? So
what if we would take the -1 out? Let the -1 stay outside, and you always keep the -1 to the end.
but from the sum or from the product, you mean?
Yeah, from the product.
Well,
-1.
on the sum side, you mean?
The sum side, yes.
Well, the issue is you cannot take -1 to the n outside of the sum because the sum depends on n, right?
Yeah.
But let's take another step. So, I mean, and that's why I'm taking it slow, because these are really error prone. Like you can make a lot of mistakes if you're not careful. That's why it is good to take one step at a time and go through these things. So when I'm writing the sum again, I will write the part that I will see at the end, at least this x part and this q squared part in front, right? So minus x to the n, I will write it here. Minus x q even, I will write it here. And divided by q squared sub n. And things with a, I'll write them in the second denominator. So in the second denominator, I will have, oh, I changed the color, but it's okay. Divided by a to the n. I didn't do any cheating, right? All the pieces are still there. On this side, these have the same product, but I will do some simplification on the top. So I will have minus x q base q squared infinity divided by minus x q divided by a and q to the power 2 sub infinity. Now, let's start taking these limits. Now, when I take the limit of this portion, as a is going to infinity, a tends to infinity, where would that go? This first factor in the product. So that thing is going to 0. So I actually have a 0 base q squared sub infinity, right? So look at the products again. So if all of these first arguments are 0, what would the product be? So this is 0, that is 0, that is 0. I only get 1 times 1 times 1 times 1. So the bottom cupo hammer is actually going to 1. Is that okay? So I don't have a denominator. Cool. So we have decided that because this thing is 1, this portion is going to 1. Now the hard part is in this limit. When a is going to infinity, this is rho going to infinity, right? What will we get? So a is going to infinity. I have a q squared sub n, a base q squared sub n divided by a n. Now I will first off get a -1 to the n. Is that okay? Yeah. -1 to the n. And then I will get a q and n minus 1 over 2, but my q is q squared now. My base is q squared. Right? So here, instead of a q, I have a q2. So it is a q2. So that is going to cancel this factor out. So I will have q to the n minus 1. So I end up approaching to this term. Now we will do the simplification. So this negative is going to cancel that negative. This q to the n will take care of that -1 over here. So I will have a n squared. Right? So that is how we prove it. We did it last week too, but I mean, it's really good to do it again because we meet only once a week. So it is almost like, well, 2 steps forward and 1 step back. Okay? So with this q binomial theorem, we made a couple of examples. And the point was whenever we see something divided by 1 Pochhammer is equal to a product, the generating function identities that we got, we could prove using Q binomial. All the examples that we did, we proved them by Q binomial, but we couldn't prove this guy. This is already a homework to construct this combinatorially. So Q n and goes to infinity is, so we wrote this sum, q to the n squared divided by q base n to the power 2. Actually, we have two q cohammers on the bottom, right? Is equal to the generating function for the partitions. We couldn't prove this because the q binomial only has one q cohammer underneath, so I couldn't introduce the second q cohammer. So we needed some new technique to do that. So in the homework, if you look at that, you would even see that we have plus an mn and even an xn, and here one of them has an xn. I guess one of them should have a plus m. But forget about this plus m portion. Let's focus on this x to the n. So I have an x to the n. And in one of them, I need to have an x. And that would be an x here. So x is keeping track of the number of parts. This is also given as a homework to prove it combinatorially, but we want to prove something that is coming from the basic hypergeometric series that can actually imply this. So we want to give a proof of this finally in this class, okay? But still, to do it with combinatorial construction is a homework. And it's super easy. You just need to think about the Durfee squares. Just to give you the hint. And Krish, when I gave it as a homework, already gave some hints on the board. Homework is the combinatorial version. We want to do it using analytics today. So for that, I want to have a formula which has two q cohammers underneath. Okay, I need two q cohammers, and for that I will define Highness transformation. So Highness transformation, and we will prove this. So Highness transformation starts this way. So you have an A base Q, B base Q sub n product. So you have A base Q sub n, B base Q sub n, divided by a Q base Q sub n is C base Q sub n. So you start with two q cohammers on the top and two q cohammers on the bottom. And you still have this z to the n, one argument, one factor. And this sum transforms into a B, then an AZ base Q sub infinity, divided by a C, a Z base Q sub infinity, and another sum. So this is a transformation formula. It doesn't sum up. It doesn't become a product already itself, but it transforms into something. It is C over B Z sub Q sub n. Again, it's a sum over n. Q A Z up base Q sub n and a B to the power n. Good, right? So, and once again, to remind you what this thing is, A1 all the way to AK, but I will do it with AB is Q sub n, is just product of two cohammers. So I have A base Q sub n, B base Q sub n. And here, this is also two cohammers. So B base Q sub infinity, A base Q sub infinity, okay? Now, we'll prove this. It's not so bad. But to prove this, we will use the Q binomial theorem. Plus, it already hints that we might need the Q binomial theorem, like right here. Do you see this portion? AZ base Q at Z base Q, that is the Q binomial theorem in its core, right? Oh, yeah. So here is that AZ base Q. Can I take it back? No. Okay. So this has a shorter proof than the Q binomial theorem itself, but we will use the Q binomial theorem. So let's do that. Okay, we start with this left-hand side. A, B, Q sub n divided by Q, C, Q comma C base Q sub n, Z n, and greater or equal than 0. Then what we want to do is we want to have this B sub Q infinity and C sub Q infinity. So if I pull it out, B sub Q infinity and C sub Q infinity. I didn't touch this A. A base Q sub n is the same. That Q base Q sub n is the same. However, and Z to the power n is the same. However, for me to make the C base Q sub n into a C base Q sub infinity, I need to add infinity many things, right? I mean, I need to add many factors to this. So what have I added? This C base Q sub n was C base Q sub n was going all the way from 1 minus C to 1 minus C to the Q n minus 1, right? Is it behind me? Should I move? So for me to make this an infinity, I need to finish the tail of this. So I need to start from giving it everything from 1 minus CQN and up. So I need to multiply this guy with this portion, the tail end of it, and the tail end of it is CQ to the n base Q sub infinity. So for me to make the CQN into this, I need to multiply it with the CQN Q infinity. So if I multiplied it on the bottom, if I multiplied it in denominator, I need to keep it paired, and I need to also multiply it in numerator, right? So I need to have it here as well. CQN Q infinity. Oh, yep. So that if you take it back in, things cancel out and you would get that CQ sub n. Make sense? I'm just trying to keep it fair, no trickery. Same deal. I need to fill up this BQ infinity. And for me to be able to do that, I need to multiply everything with this BQN sub Q infinity on the top. So I divide it on the bottom. Okay. Perfect. Now, so let's write this again. I have an A Q sub n. I have a Q sub n. I forgot the front factor, Z n. And I have this C Q to the power n, Q to the power sub infinity. And I have B Q n, Q infinity. There's this front factor that I forgot. That is the product of B sub infinity and C sub infinity. That is the front factor that is here. Cool. Now, there's an infinite sum inside my infinite product inside my summation. And this infinite product looks like it is something, one cupo hammer divided by another cupo hammer. Can I expand it using the Q binomial theorem? Would it be possible? So can I open it up as a sum using the Q binomial theorem? If you look at the Q binomial theorem, my Z, it was AZ over Z. Q binomial was AZ over Z, right? For me to write this as a Q binomial, my Z of the Q binomial theorem should be BQN. And my A AZ over Z, right, should be C over B. So that AZ would become CQN base Q infinity, and Z Q infinity would be BQN Q infinity. So we write this thing as a double sum now. The front factor BQ infinity divided by CQ infinity. We have the first sum and greater or equal than 0. I will copy it onto the next page. So the things on the inside are the same. So this portion stays the same. Now I have a second sum in M where we write these Q binomial theorem. So this is the Q binomial with these selections where A is C over B divided by M. We have a QQ infinity, QQM, and I will write it again on the next page. BQM is going to be the last one. And BQN to the M is going to be the last one. Let me write it properly on the next page. We start with this guy, A, B, base Q sub N, Q, C, base Q sub N, Z to the N, and from greater or equal than 0, we write this step. We filled these products up so that we have the infinite products outside, and greater or equal than 0, A, Q, N, Q, Q, N, and a Z, N. And this ended up giving us a C, Q, N sub Q infinity, and a B, Q, N, Q infinity. Now the idea that we caught was that this is an infinite product over product. We might as well use Q binomial theorem. So we use Q binomial theorem with Z being BQN and A being C over B. So this is the A and Z of the Q binomial theorem, not the A and Z here. And with that, we wrote this product over product as another sum. BQ infinity, CQ infinity. This sum is there. A. And do you know what trickery I will do once we have double sums? Exactly. Whenever we see a double sum, it is always good to assume that everything converges uniformly, absolutely however you like, and we can make this convergent. I'm working under the assumptions of that. Then switch the order of summation. Let's see if something is going to sum up for us. So if we write this in, the Q binomial theorem is going to have this C over B is Q sub M this time, divided by a Q QM, and that's Z B to the power BQN to the power M. And we will switch the order of summation. We would like to switch the order of summation. So whatever is only related to M, I will carry it in the first sum. Whatever is related with N, I will keep it in the second sum. And the front factor is the same. Now the M sum is outside. So this term only depends on M. This term only depends on M. I can take them out. C over B, QM, QM. That's B to the power M. I can take it out. But this QN, it depends on N too, so it will stay. That was a great sigma. Now we have the second sum, which is N now, right? So we have QQN, AQN, ZN, and the QM to the power N. Well, perfect. So we have an M sum on the outside and N sum on the inside. And do you see what we can do with this inner sum? Any ideas? There's one polymer on the top, a q polymer on the bottom, and a factor to the power n. So what do you think we will apply again? There is another q binomial, right? So this is the sum side of the q binomial, that z is replaced by z to the qm, and a is replaced by just a. So we will apply this q binomial once again. So this is the infinite product, this is the infinite product. The same sum, and the summation of this, I will again need to copy it to the next page, I guess, but the summation of this will be az base q sub infinity. A times z is a z q to the m base q sub infinity, and z on the bottom we have z qm base q sub infinity. So this infinite product depends on m, but at least we were able to get rid of one of the sums. So let's again, just for the last bit of the proof, write what we have proven. We started with this, and this is the only issue with these virtual boards, that I'm having a really hard time keeping it small and running out of space. Okay, so what we learned is we have b q infinity divided by c q infinity, and we end up getting the sum. On the inside we have a c over b base q sub m, a q base m, and goes from 0 to infinity, a b to the power m, and we use q binomial theorem to get this sum, get the sum turned into a product, a z q m base q sub infinity, and z q m q sub infinity. Okay, perfect. We're almost done. Really, this is going to be the last board to finish this proof. Now I have these infinite products, which is not useful to me, because these sums, these products depend on m. So would I be able to maybe fill in this product again, so that I can take that infinite product out? So what should I give this bottom one? So I have this z q m q infinity. What should I multiply this with, so that it becomes a z q infinity? If this is the case, if I have z q infinity, it doesn't depend on m, so I can take it outside of the sum. So what should I multiply my z q m q infinity, so that it becomes z q infinity? So I should start from this zq, right? I mean, so this is where we end up. This starts at 1 minus zqm and goes all the way up. So I need to go all the way to this zqm. So what should my bottom subfactor be? This is infinity. So in this one, I start with 1 minus z. So I already start with q to the power 0. And we want to go all the way to 1 minus z q to the power m minus 1, right? So how many factors do I have in my product? M factors, right? There is one tiny thing that always gets mistaken, that you start with the z. So you're right that we want to go all the way to q to the m minus 1, but we need one more product. So if I multiply my factor with this zq base m, this thing on the bottom becomes that zq infinity that I wanted, and I can take it out. Well, but mathematics works in fairness. I mean, we gotta keep it fair. We gotta keep everything the same. So I need to multiply and divide with the same thing, right? Now, if I do this, everything is equal again. On the bottom, I have this infinite product, but I mean, I didn't do anything. I just multiplied and divided with the same thing. So it is 1 on the inside. Do you see it? Perfect. So now I can take this bottom denominator product outside, and I can do the same thing on the top too, right? For the top factor, again, goes all the way to Qm. So I would need to have this AZ Q sub M, because with that, these two combined would give me AZ base Q sub infinity. It doesn't depend on M. I can take it out of my sum. But right now, I just multiplied the numerator with something. So I need to divide with the same thing to keep everything the same, right? Perfect. Now, this factor on the bottom, I will use it to combine with the other cubohammer so that I can take that cubohammer outside. The top cubohammers, these two, I will combine them so that I can take it out. Perfect. Then what we will see is on the top we have B Q infinity. Now we have an AZ Q infinity as well. On the bottom, we already had CQ infinity. Now we will have a ZQ infinity as well. And what is left in the sum? From 0 to infinity, we have this C over B, and then Z base Q sub M. Right, we use this cubohammer, we use that cubohammer, but this one and that one stayed inside. Still, they're there. They have the subs to the M. And QQM, we have that, and we have AZ. This Q sub M, and the Q factor that we see is B to the power M. And this is the highness transformation. That's all there is. So we use the Q binomial theorem in two ways. We need to fill in the infinite products, and we need to use the highness theorem in two ways. So this sum becomes a front factor and a similar, really similar sum. And this is really useful. It's incredibly useful that you see your sum in a way, but sometimes you don't understand that you can have a good grasp of it. So what you do is you use highness transformations or other transformations to massage it into a form that you can interpret better. So I want to say this, this one more thing too. We could have picked A and C in the beginning. So we picked B and C, right? We picked B and C and pulled them out. We could have picked, I mean, C, the choice of C is always the same because the other one is a QQ sub M. And you would always see this one QQ polymer in the basic hypergeometric series. It was the same as the Q binomial theorem. It was always that Q, Qn, and something else maybe. So the choice of C was obvious, but the choice of A or B was just a selection. And picking A would give us the similar thing, right? Now, look at here. We have a similar transformation again. We have a similar sum again, right? If we want to apply highness transformation to this guy again, we can do it. Now the C in this choice would be AZ, right? The B choice, whichever we want to apply, can be C over B or can be Z, right? You can either but it doesn't really, and that's a good point. Well, just think of it as a closed box, and then you plug in C over B, okay? Yeah. Then you plug in C over B. It's almost like that was A, and then we plug in C over B. So right now, I'm taking this as the left-hand side, and I'm trying to apply this transformation once again, right? The choice of C is obvious. The choice of C has to be AZ. If the Q is there, and the C is now replaced with AC. But the choice of B, you have two options. You can either choose B to be C over B and apply this, then you're applying this transformation, or you can choose your B to be Z and apply this transformation, right? And you would see that you have different paths. And I will leave that as a homework. So apply this transformation again. Apply Heine again. With the choices that B is replaced with CB and C is replaced with AZ from here. Just you have this, take this sum, use the Heine transformation, plug this in to see what you will get. And the other one is the C is the same, but B is Z. And what you will see is in one of the transformations, you would get back the original thing. In the other one, you will get to another thing. So Heine actually has three transformations, but essentially it is the same transformation. But with different choices, you can get three different transformations. So apply Heine multiple times, and this is a good excuse to do that. You can apply Heine multiple times. All right. We proved Heine to be able to prove that one combinatorial thing that we wanted to prove, right? So for that, I want to see first a corollary of Heine. If you were to pick Z to be C over B, if you have a C over AB, then your sum AB base Q sub infinity Q C base, and this is also n. AB equals n divided by QC base Q sub n, and C over AB to the power n. You would end up getting this product: C over A, C over B, is Q sub infinity, and C over AB is Q sub infinity. No sum side, just the product. If you were to pick that Z to be C over AB in Heine. We can prove it easily, but let's look at a corollary of this corollary first. Now, if you take C to go to Q, so I have Q, Qn, and another Q, Qn. I have two of them. And if you were to take what do I want? Yeah, okay, this is Q, Qm. If you want to take A and B tend to infinity, so I have A Q sub n divided by A to the power n, that is one of the limits. B Q sub n divided by B to the power n, that's the other limit, right? If you were to do that, this sum side on the left will turn into the Q n to the power 2, and you would have Q n to the power 2. And on the right, C is Q. So on the bottom, I have a Q sub infinity. And let's convince ourselves the rest are all ones. So Q divided by A, but A goes to infinity. So this goes to 0. It vanishes. Q divided by B, B goes to infinity. That goes away. It vanishes. It is just 1 in the product. C over AB, A and B are both going to infinity. So that guy goes also to 0. So that guy also goes away. So we end up getting 1 over q to infinity. Is that okay? All right, perfect. So this theorem that we wanted to prove combinatorially is a corollary of Heine. So you prove something more general, you can reduce it down to things that you wanted to prove. If you want to include that x to the n, then you presumably needed to start with another x here. And yeah, this is also in the lecture notes that I included. That's how you would recover that. So would you like to see this, the proof of the corollary? Yes, no, maybe, sure. Okay, so we will use Heine's theorem for the proof of that. Proof in Heine, I will just plug in z equals c over ab, right? So in Heine, when I plug that in, the left-hand side becomes that. And Heine's theorem, Heine's transformation says that the right-hand side would be z is that, so we have a b, then an a times z, so a times z is c over b, so infinity. I'm just using the Heine's transformation formula that is on the previous page. I'm just plugging in the things, so c, then we have a z, which is c over ab, is q sub infinity. Cool, and we have the sum, and greater or equal than 0. Now we have a c over b, and z, my z is c over ab this time. C over ab is q sub n divided by q a times z, which a times z is also appears here. That is the c over b is q sub n. And my last term is b to the n. Now in this transformed sum portion, we see a repetition. So c over b base qn and c over b base qn appear both on the top and the bottom. I can cancel them. So this became a 1 q polyhammer on the top and another q polyhammer on the bottom with an argument, a q factor. I will start calling that. So this is a q binomial theorem. Right? I have 1 q polyhammer divided by another q polyhammer with a factor. So I can sum this up. The q binomial would be az on the top. Az is c over a base q sub infinity. Az base q sub infinity divided by z base q sub infinity, b q sub infinity. Right? Let's carry this front factor in. B c over b base q sub infinity c over ab is q sub infinity. Great, right? This b q sub infinity appeared on the top and on the bottom, so I might as well just cancel those, and that should give me what I need. So on the top I have cb base q sub infinity, ca base q sub infinity. I have two products, just as the corollary suggests. And on the bottom, I have c and c over ab base q sub infinity, right? This is what we wanted, the same product vectors. So it's done, right? Cool. All right, now, let's do one more strong sum equals to product type identity. And I promise we will go back to the partition theorem really soon. But we need these techniques to be able to prove some stronger results. And this one is really strong. And after this, we will start applying this to multiple things that we know. And one of them is going to give us the Euler pentagonal number theorem, which we have already covered many lectures before. But we kept it vague. We said that when it's a pentagonal number, difference between the distinct partitions into odd parts, into odd number of parts, and the distinct partition to even number of parts differ by 1, but we never said when the difference was more on the odd side, when the difference was more on the even side. We just said that absolutely the difference was 1. With Jacobi triple product identity, it's what we will prove now. We will be able to just see it as a series. We will say that a negative 1 to the n term, which will tell us when we would get a negative value or a positive value. Okay, that's one of the applications that we will get at the end. So Jacobi triple product identity. There are many forms of this triple product identity, all equivalent. I will write the simplest form on the sum side. So this is a bilateral sum. We take it, the sum all the way from negative infinity to positive infinity. That's a difference than what we have seen before, right? And inside the sum, I will have a simple, what is called a theta series. It is z to the n and a q to the n to the 2. That's it. No q parameters, no nothing. I have a z to the n and a q to the n squared. And this would be minus zq minus q over z. So it is symmetric in z, z going to 1 over z if you will, comma q to the power 2 base q to the power 2 sub infinity. That's it. So zn q to the n squared is minus zq minus q over z, q squared infinity. So 1, 2, 3 products. That's why it's called the triple product identity. So you have 1 q per hammer for minus zq, 1 q per hammer for minus q over z, and 1 for q squared infinity, and this is it. Now, for this proof, we will use pretty much everything that we have seen so far. Actually, mostly Q binomial and one formula that we discussed in the beginning of class. And I will try to keep it quick. You start with one of these products. I will start with minus zq. If you want to start with minus q over z, just take it, z goes to 1 over z. Doesn't matter. So you take this minus zq base q squared sub infinity. This can be written using Q binomial theorem, right? Or not even that. We can use Q binomial theorem, but I mean that's why I mentioned this term in the beginning. An implication of the Q binomial theorem is what I want. I directly want to use this formula. So minus zq q squared is what I want, right? So I will use this formula. So zn q to the n squared divided by q squared n. This is literally what we wanted. We already proved it once today. So this is the sum n from 0 to infinity, z to the n, q to the n to the power 2 divided by q to the power 2, q to the power 2 sub n. Right? This is what we just mentioned. Now, I want to use the similar trick. So after all, I want to have a q squared infinity on the left-hand side, right? So I want to pull that q squared infinity to begin with, so that I can multiply to the left-hand side when I want to. If I want to pull this out, how should the sum change? How should the sum ends change on the inside? Now, this zn or q to the n squared are not going to get affected, but I completed this product, q squared n, I completed that. So what did I multiply this with to make it into a q squared infinity? This goes all the way from 1 minus q to the power 2 to 1 minus q to the power 2n. So I must have multiplied everything from 1 minus q to the 2n plus 2 on to infinity, right? So that is the factor that I multiplied with, so which was q to the 2n plus 2 base q squared sub infinity. So I must have multiplied the bottom with this. To keep everything fair, I need to multiply the top with that. Right? So logically, nothing really super hard. It's just we need to do really good bookkeeping. And that's it. So, okay, we now massaged our sum. We already start seeing the piece that we want on the right. We already started seeing pieces that we want on the left. So we already have this first thing. We already have the second thing. Somehow we will just make this sum into a bilateral sum because this is from negative infinity to infinity. This is only from 0 to infinity, right? And then also collect this term somehow. Now, let me take care of this bilateral portion first. If n is negative, if n is negative, a negative integer, n is a negative integer, I'll make this claim. Q to the 2n plus 2 base q2 sub infinity is always 0. Are you okay with that? Let's say n is negative 10. So I end up getting q to the negative 20 base q squared sub infinity. So it says I start with 1 minus q to the negative 20. And I take steps of 2, add 2 at each step. And I will do this addition infinitely many times. So if I start with a negative n, I think it is fair to say that I will reach 1 minus q to the 0 at some point. 1 minus q to the 0 is going to be 0. It is going to just swallow everything up, right? So instead of going from 0 to infinity, I might as well just write the sum just as is, without changing anything, but say that this sum is all the way from negative infinity to infinity. Cool, right? Z n q to the n squared and q 2n plus 2 q squared sub infinity. See ya. All right. Now what? Now we might as well. We're trying to get rid of this thing, this term, right? So everything that we wanted is here, but except for that one portion. We made it a bilateral sum and goes from negative infinity all the way to infinity. Can I use the same formula that we used to connect these two, product and the sum, here, with a special choice of z? Can I write that thing as a sum again, as a second sum? So that it's a double sum, then I will flip the order of summation. So for me to make this minus zq q squared sub infinity into q n 2n plus 2 base q squared sub infinity, what should I pick z to be? What should z be? So that I can use the same formula that is here. So here, if I want to apply this one formula, which I will put a star here, if I want to apply this equation again, in this star, z has to be minus q to the 2n plus 1. Right? Perfect. So let's do that. 1 over q squared sub infinity. I have this bilateral sum, negative infinity all the way to infinity, zn q to the n to the power 2. Then I need a new name, so m greater or equal than 0. This is not a bilateral sum. This is a single-sided sum. It goes from 0 to infinity. Now, instead of z, I have a negative q to the 2n plus 1, negative 1 to the m, q to the 2n plus 1 times an m, that is the z to the m. This is an m. And the q to the m to the power 2. Right? That part doesn't change. And divided by a q squared a q squared sub m. Perfect. Now, what we will do exactly is we will switch the order of summation again. Yes, we will switch the order of summation. I see the trickery that was needed once again. So infinity, sum m goes from infinity 0 to infinity. And here I have a -1 to the m, q to the m squared plus m. This portion depends on n, so I cannot really take it out. Where did my m squared go? Ah, okay. Well, it's a little bit more tricky than that. Let me still write everything down, but I want to write them selectively. So I will take this portion out. So q to the m is out, but I will leave that m squared portion inside. And you will see why. And that 2nm inside. So now n is from -infinity all the way to infinity. I have a z to the n on the inside. That was that. I have a q n squared plus 2nm. That 2nm came from here. And plus n m squared. Because I selectively decided that this should stay on the inside. No other reason. I could have plugged that in. I could have plugged that out, but I kept it inside. So on the inner sum now, I end up getting z to the n and a q to the n squared plus 2nm plus m squared. So what is n squared plus 2nm plus m squared? That is a perfect square. Yeah, that's a perfect square, right? So this is actually an n plus m to the power 2, right? If only this thing was not n. Thank you. Yes. So q squared m, I took it out as is. Nothing changed, yes. As I'm saying, great bookkeeping is needed. But here, the last bit of the trickery is that we ended up getting, I'm just copying this bottom portion here. We end up getting 1 over q squared infinity, sum -1 to the m, q to the m, divided by q squared m. This is one-sided. M goes from 0 to infinity. And on the inside, we have z to the n and a q to the n plus m to the power 2. And n goes from -infinity all the way to infinity. Well, you see, if only I had n plus m on top of z, I would just name it a new thing. Because n goes from all the way to -infinity to positive infinity, that new thing, let's say k, would also go from -infinity to positive infinity. Because m is fixed for that sum, and n varies. But right now, I cannot really do that directly, but maybe I can do this trickery. So why not add this plus m, just artificially? So to keep things fair, I will need a minus m outside. Is that okay? Well, great. Then this inner portion became a new k from -infinity to infinity, z to the k, q to the k to the power 2. Again, the thing that we are looking on the left-hand side. Now, what is that? And regardless of m, this is always the same. So I actually untangled them. Take the m, this is the same sum because n goes from -infinity to infinity. So that can always be factored. And what about this guy? So I have -1 to the m, I will even write it like all together. So negative z q to the m divided by q squared sub m, and this 1 over q to sub infinity. Here at the very last step. So what is this sum?
Why you put z2 into square, but here z in minus m?
Oh yeah, that's z should be 1 over. Yes, you're right. It's q over z. It is this factor, but I just made the mistake. Yeah, thanks. Let's write it correctly. So minus q over z. So what is that sum now? Don't be shy. It is going to be the same term again with a equals 0. That is the q binomial theorem with a equals 0 on the top. So it is this one front factor is the same. Q binomial az over z. A is 0. So on the top, I don't have anything. I just have 1 divided by z base. My base is q squared this time, base q squared sub infinity times this bilateral sum zk q to the k squared. Well, look at that. On the far left, I have minus dq q squared. On the far right, I have my q squared infinity. So I have this. In the denominator, I have that. So if I carry it on the left, I would have that. And if I carry this to the left, I will have this, right? And whatever is left is the sum that I'm looking for. I mean, I know it's a really long way, but that's it, right? So now we have Jacobi triple product identity. Perfect. Yes. Perfect. Now, actually, we have done most of the Q series that we need to do. So we might as well just enjoy what this gives us. So let's look at some corollaries. Do you have any questions about this? Again, the motivation is as a technique, like basic hypergeometric series or hypergeometric series are really strong to get summations. So we're trying to build an arsenal. So whenever we are stuck, we can try to use some stuff from them. And they will be needed. So combinatorics will not always be useful. And we already got stuck with combinatorics in some terms beforehand. Well, now we built enough basic hypergeometric series for now. So yeah, let's enjoy. The first thing, -1 to the n q to the n to the power 2, and from minus infinity to infinity. This is due to Gauss. Both are due to Gauss. So Gauss sums -1 to the n q to the n squared. We already know that this is Jacobi triple product identity. We can massage this and write it as q sub infinity divided by minus q sub infinity. So it is reciprocal of the over partitions, which Gargi would know the name. We don't need to know it by now, right? This is minus q over infinity, q infinity, but it's just the reverse order. That's one. But you take a series, it becomes a product. Very nice, right? Another one-sided. N is 0 to infinity of the triangular numbers, and plus 1 over 2 is equal to q squared sub infinity q squared sub infinity. Was this one-sided or double-sided? I should check that again. I believe it was one-sided. So how? So the proof of the first one should be easy, right? Proof of the first one, pick z to be -1 in JTP. In Jacobi triple product identity, so that you get the sum to be the same. Then it becomes a minus z becomes a q, minus q over z becomes a q, and then a q squared and a q squared sub infinity. So I will look at the last three. It is q to the power 1, q to the power 2, base q to the power 2. So it is 1 modulo 2 parts and a 2 modulo 2 parts on the top. So forget about the first one. The other two is 1 modulo 2 parts and 2 modulo 2 parts. So it is all 1 modulo 1 part. So that is q infinity. That's how we would combine it. This is 1 modulo 1 parts, infinity many. Now this q squared sub infinity, we can handle it in multiple ways. One way to handle that is we can use the same trick. Let's multiply top and the bottom with q squared sub infinity. Now I have 1 modulo 2 parts, 2 modulo 2 parts. On the top, I have another q infinity. On the bottom, I have q squared. So I have a q infinity, another q infinity. And on the bottom, I have a q squared sub infinity. Now, think about the factors of this q squared. I have 1 over 1 minus q squared. 1 over 1 minus q squared, 1 over 1 minus q to the 4, right? These are all differences of squares, right? So 1 minus q squared, I can write that as 1 minus q, 1 plus q. Always, I can just split it two ways. This guy, I can split it as 1 minus q squared, 1 plus q squared. So if I were to do this splitting over and over again, I will collect a q infinity, and I will also collect a minus q infinity. Right? So this is the same as, so q infinity, q infinity, and on the bottom I have a q infinity, which is the terms with the negatives, and I have a minus q infinity, which is the term with the positive, so they cancel out. We got the proof. Q infinity divided by minus q infinity. The second one. I do believe this is 0. So that's it. Okay. So we start with this infinity q n plus 1 over 2. And I want to add whatever is missing to this. So this is what I'm interested in, but I want to add everything from negative infinity all the way to negative 1 of the same term. So if I were to add that, I will have the bilateral sum that I can use the Jacobi triple product identity to. But I can also massage this, right? I mean, so n goes to, yeah. So let's do the Jacobi triple product identity first. So this is the addition, not the term that I want, but the addition is Jacobi triple product identity. And for that, for this division by 2, I need q goes to q over 2, right? And for that plus 1, z has to be, so this is q goes to q1 over 2, or q squared goes to q1, and z goes to q1 half again, right? So that combines z and q to the n squared turns into a q n squared divided by 2 plus an n over 2. That's literally the term. So let's write what the right-hand side of the Jacobi triple product identity should be then. It is minus z times q which is Q, but minus Q, and -1. Perfect. Yes, this is what we wanted to see. And Q squared goes to Q, so there is a Q and a Q sub infinity. So this is the term. That is a product. Minus Q, -1, Q base Q sub infinity. Now let's see that this is 2 of something so that maybe we can simplify this. I can switch this sum, right? I mean, n goes to -n. I can switch the sum and write this as n all the way from 1 to infinity of Q to the -n plus 1 divided by 2. Cool. Let me modify this a tiny bit. So -n, I will put this minus inside. So this is a plus n and a -1. So n -1 over 2. Is that okay? Now, can I take this n and switch it back to 0? So n goes to n -1. How shall it change here? So these n's should be shifted up once, right? So this n would turn into n plus 1, this first one. This n -1 would turn into n plus 1 minus 1. So it will be n, but I will start from 0, but this would be a plus 1. Now look at that. I get 2 copies of the same function. Well, perfect. Then what we learned is that 2 copies of that, two copies of that n from 0 to infinity sum of Q to the triangular numbers is minus Q and -1 a Q base Q sub infinity. This portion came from the Jacobi triple product identity. That 2 came from that switching. What is -1 base Q sub infinity? Or what is the first term of that? Let's focus on that. So -1 Q sub infinity. This is 1 minus -1. Then 1 minus -1 times Q. 1 minus -1 times Q to the power 2. So on and so forth, right? So this first term is 2, and the rest is just a 1 plus Q, 1 plus Q squared, 1 plus Q cubed, 1 plus Q fourth. The rest is just minus Q sub infinity. Well, perfect. That 2 and that 2 will take care of each other, right? And we will get the sum and from 0 to infinity, Q to the triangular numbers n plus 1 divided by 2 is equal to minus Q, another minus Q, a Q sub infinity. What do we need? We wrote this in a different way. We wrote this as a Q squared sub infinity divided by a Q squared sub infinity. I will use 2 things. I have 1 plus Q here, 1 minus Q in this guy. I can combine them just the other way around. I have 2 pieces of the differences of squares. So 1 x minus y, x plus y, it is x squared minus y squared, right? So if you combine these 2, minus Q plus Q base Q, that is a Q squared sub infinity. Cool, so that front top portion is gone. Now, what is this generating function? Minus Q base Q sub infinity is the generating function for the number of distinct partitions, right? What did Euler's theorem say? Euler's theorem said the number of distinct partitions is the same as the number of partitions into odd parts, and the generating function for the partitions into odd parts is 1 over Q squared sub infinity. Not the only way. You can multiply top and the bottom with Q infinity again, and then do the tricks. Oh yeah, so we have this one too. So nice, right? I mean, Jacobi triple product identity directly takes us from a sum, a simple sum with no Q programmers inside, even a sum with not much going on, a sum you would usually call a theta series, into an infinite product. And let's do it for the Euler pentagonal number theorem and finish the day. And next time we will come and do Roger Somanjan, like with some really core partition theorem. So this is Euler's pentagonal number theorem. And that says the sum and from negative infinity to infinity, q to the power n 3n minus 1 divided by 2. So q to the power a pentagonal number times a negative 1 to the n is equal to q infinity. Perfect. We will do the pentagonal number, we will do the differences interpretation just in a second, but let's prove this. For me to prove that, I will use Jacobi triple product identity again. And for that, I have a 3n squared divided by 2. So I have a q3 over 2n squared and a minus n over 2, right? So for me to get this 3 over 2n squared, my q squared that I have should go to q to the 3 over 2. My qn squared inside my sum in the Jacobi product identity should go to q3 over 2n squared. So this directly tells me that q in my Jacobi triple product identity should turn into q3 over half, 3 halves. And for me to get this negative 1/2, z has to go to a q to the negative 1/2, so that that portion comes in. And for that negative, I need z to be a negative. I'm just matching the formula that we proved with what we have, right? So once we do that, once we make these choices for the Jacobi triple product identity, the Jacobi triple product identity here would say you have minus z times q, minus and minus, they go away, minus z times q is q to the negative 1/2, q to the 3 halves, it is q to the 2 halves, so q, comma, minus q over z, again the negatives go away, q to the 3 halves minus minus 1/2, so it is q to the power 2, comma, q squared, so q was q 3 halves, q squared is q cubed, right? Comma, the same q squared, q cubed sub infinity. So this sum is apparently that. Is it that? Can you see that it is? I have 1 modulo 3 parts, 2 modulo 3 parts, 3 modulo 3 parts. So it is 1 modulo 1 parts, all the parts. Super simple, right? So do you see that this is a dissection of that product? So this is 1 minus q, 1 minus q4, 1 minus q7, 1 minus q10. It is 1 modulo 3 parts. This is q squared, q5, q8, so on and so forth. This is q cubed, q6, q9. Combine them all together, you have q1. So this proof is super simple. Now that we have Jacobi triple product identity. Let's do the interpretation of that then. And that should be our last bit. Now, remember that minus xq q sub infinity, which I will turn it into my q sub infinity. This thing was partitions into distinct parts. You take all the partitions into distinct parts. The x counts the number of parts in your partition. And the size of q, size of the partition is counted by the exponent of q, right? If I were to plug in x being -1, which is essentially what I'm doing here. If I were to plug in x being -1, this would turn this right-hand side into the generating function with a weight. So I will have a -1 to the number of parts. And q that, right? I take a distinct partition, which I will call that set to be D. Now I weigh the number of parts, -1 to the number of parts, right? This is the product of QQ infinity. That is the interpretation of the product QQ infinity. So this is the same thing as if my partition is into distinct parts and the number of parts of the partition is even, I have just the weight being 1, so I count them positive with a positive weight, then a minus, I have partitions into distinct parts, but the number of parts of the partition is odd. Is that okay? So let's give a name to these, the number of these partitions to be P distinct even of n, and give the number of partitions into distinct partitions into odd number of parts to be PDO of n. So I have this QQ infinity giving me the sum where the difference is PDE of n minus PDO of n, and I have Q to the power n, which is the partitions, the numbers that I'm partitioning. Right? So the product of the Euler pentagonal number theorem is the difference without the absolute values now of the distinct partitions into even number of parts and the distinct partitions into odd number of parts. So if I compare it with the left-hand side of the sum, we would know the signs. And that's all there is. That's really all there is. So if we were to just look at that, we say that this -1 to the n, q to the 3n minus 1, n over 2, and from -infinity to infinity is this q infinity is equal to the sum P distinct even when I'm partitioning n, the number of distinct partitions of n into odd number of parts, into even number of parts, q to the n. I will compare the right and the left. I can even manipulate this -infinity to make sense. So let's split it at 0. So I can split it at 0, 1 plus, I have everything from 1 to infinity of the same thing, -1 to the n, q to the 3n minus 1, n over 2. I can have everything from negative infinity to 1. I can flip that and change these n's to negative n's. Again, -1 doesn't get affected. And then I can combine. And with that negative, you would have a plus here. So the combination would be, you would get a 1 plus q to the n here is equal to these guys. So now, yeah, we can one-to-one compare and see that this is actually the case. If you're looking at any n, any integer n, and if you look at the difference between the number of partitions of n into distinct parts, where the number of parts is even, minus the number of partitions of n into distinct parts, where the number of partitions are odd, this is either this term, -1 to the n, if the size of your partition pi, the size of the partition of n to be n, I should write it with m, 3m plus or minus 1 divided by 2 for some m. So either your size of the partition is n, this is n, and this is n. So I already fixed the size of the partition to be n. So if your size of the partition is plus or minus m 3m plus or minus 1 over 2 if it's in that format. This one, that is the plus 1 portion of it. Oh, come on. So you either have your -1 to the n, or I should write it with m's now so that the m's would correspond to what we're writing now. So if your size is n, you compare it with the left-hand side, right? So you need to have either your q to the 3m minus 1m over 2 to be exactly n. Either it is n is equal to m 3m minus 1 over 2. Then you get the weight -1m. Or your n needs to be this times m, which is m 3m plus 1 over 2. That plus m makes us -1 to a plus 1. You see this 3m squared minus m over 2. This is 2m over 2, right? So if if the number that you're partitioning n matches one of these, you directly know the difference you will get in this is -1 to the m. And if your number doesn't match that, if you have any other number, well, look at the sum. There is nothing that this sum can give you. That is a 0 otherwise. Because there is no, like, if n doesn't match a pentagonal number, then this sum is 0, right?
People get +1 instead of -1 because either we add those m or we multiply. Sum. Okay.
So this m is multiplied.
Yes.
So here this is multiplied on the inside. What I do is couple of steps. Yes, let's do that here.
But since you multiply twice, those terms.
One is in the power, one is not in the power. So I should write it here. So 3m minus 1 times m over 2, or let's write it even here. 3n minus 1 times n. I will write this m as well. This is 3m squared minus m over 2, right? Then, now we split it into 3 parts. That is where I rushed. I didn't want to take too much of your time, but now we're past that point anyway. So apologies for that. I split it in 3 parts. One is m is equal to 0. That is, you just get 1. Plus, you have m is positive. That is, you get the same sum, m from 1 to infinity of the same sum. Q to the 3m squared minus m divided by 2. Then you have another portion, which is m is negative, which is plus. You have this m is everything from negative infinity to -1. And the same sum. Uh, 3m squared minus m over 2. Now, I want to combine these two, combine the letter 2. So for that, I need to take m goes to -m, so that I end up not from negative to -1, but it's 1 to negative infinity, 1 to infinity, right? So if m goes to -m, this -1 to the m doesn't get affected. -1 to -m, it's the same thing, right? I mean, it's just flipped, but it's just the sign. So this thing stays the same. What about this? M goes to -m, m squared doesn't get affected. M goes to -m, this guy becomes a plus. Yeah, that's where the bulk of the change happens. So then this guy from 1 to positive infinity, but that became plus. And now I combine them into one sum. I rushed it, and -1 to the m is there. That small factor I wrote it in front. Then it was that 1 that represented that, plus, which is this plus, q to the m is to make it to plus m, right? Oh, yeah, after all, what we get is now, whenever you see a difference between distinct partitions into even number of parts, distinct partition to odd number of parts, you can directly find what the weight is if you're going to get a +1 or a -1 using just this. Find an m that the number that you're partitioning, is there an m that where you can represent this number as m times 3m plus or -1 divided by 2? If so, whatever that m is defines that weight. If there's no m, where you can write the partition, the number that you're partitioning in this format, then the weight is 0. They're the same number of distinct partitions into even parts as they're the same number of distinct partitions into odd parts. Now, this thing leads to one more thing that I left as a homework. This is the generating function for the number of partitions. This is Euler pentagonal number theorem. If you multiply them, you will get 1, right? Nothing special. This is Pn, Qn. This is something else. From this multiplication, you can actually show that the number of partitions satisfy a recurrence where you have Pn is equal to Pn -1 plus Pn -2 minus Pn -5 minus Pn -7 plus so many, then a -1 to the m, that same m was the weight Pn minus m 3m -1 over 2 plus -1 to the m, again the same -1 to the m, Pn minus m 3m plus 1 over 2 plus . So it's an infinite recurrence, but you can calculate P of n by smaller values of P of n using this recurrence. And the only thing that you need to do is the convolution between these two products. So I left it as a homework just to show that this matches. And yeah, using this, people actually calculated P of n into great heights. Like, I mean, P of 100, I don't know what it is, but I mean, using this trick, you can presumably calculate it in 5 minutes. Okay, perfect. Yeah, let's leave it here. Let's come back. Let's start with the Rajasamanjan and prove that using Jacobi triple product identity. So the trick is for P of 100, so it is definitely a recurrence relation. P of 99 goes all the way. So after some time, this becomes a negative value, right? Whenever it becomes negative, these are 0. So you chop it off. So for this, you would do the same trick. Yeah. So if you want P of 100, you look at the smaller values and build it up that way. So it's like, it is the recurrence relation that once you get smaller values, once you get initial conditions, you can calculate more, right? But yeah, and actually these are the pentagonal numbers anyway. That's the point. So you only need to go back with pentagonal numbers. That is, the generating function of the pentagonal numbers is that guy. This is the generating function for the number of partitions. So we look at the convolution, and the convolution we know is 1. So these numbers must be equal to each other. Then you add one more value to that, saying that P of anything negative is identically 0. So although this recurrence doesn't have a finite order, for every finite number, it does have a finite order. So it cuts at some point, then you can calculate it that way. But yeah, from a syntactic point of view, from a abstract point of view, this relation is just coming from that convolution. And I mean, just do the multiplication, see it for yourself. Okay. Perfect. Yeah, sorry for taking extra time, but I'm glad that you stayed. Yeah, let's end it here.